Hey everyone, welcome back, and today let's solve Leetcode problem 2799 titled Count Complete Subarrays in an Array. So we're given an array nums consisting of positive integers, and we call a subarray of an array complete if the following conditions are satisfied. The number of distinct elements in the array is equal to the number of distinct elements in the whole array. We want to return the number of complete subarrays. And again, they quickly define what a subarray is. It's nothing but a contiguous non-empty portion or part or range of indices of an array. So in example 1, we have our input array nums to be 1, 3, 1, 2, 2. And the reason why we have an output of 4 is because that is the total number of complete subarrays. And again, let's revisit the idea of what a complete subarray really means. The number of distinct or unique elements in that specific subarray is equal to the total number of distinct elements in the whole array. In this case, how many unique elements do we have in the entire input array nums? Well, we have 1, we have 3, and we have 2. So we have 3 unique elements. How many different subarrays can we form that have 3 unique elements? Well, they could be 1, 3, 1, 2. That has 1, 3, and 2. They could be 1, 3, 1, 2, 2. The entire subarray itself can still be considered to be a subarray. And we can also have 3, 1, 2. That still has 3 unique elements. And we can also have 3, 1, 2, 2. Notice how all of these still work. We still have 3 distinct elements in each 4 of these subarrays. And these are all the 4 subarrays that have unique elements of 3. So that's going to be why we have an output of 4. In example 2, we have our input array nums to be 5, 5, 5, 5. In this case, we only have one actual unique integer, that's 5 itself, and so any subarray that we choose is going to be complete. Why? Because any subarray that we choose, it's always guaranteed to have one and exactly only one unique element, and that's going to be the only unique element that we have, regardless of which subarray we pick. That's going to be 5, and we know that there's 10 different subarrays that we can choose from, or 10 different subarrays that we can actually form the entire input array, and so that's why we have an output of 10, which are all going to have exactly one unique integer of 5. So for the constraints here, we see that the length of our input array nums is actually going to be between 1 and 1000. It's actually rather small input constraint, kind of giving us a lot more room to work with, right? And for every value in the input array nums is going to be between 1 and 2000, so not too bad of input constraints. And yeah, so let's go ahead and lead into the main observations that we can really make. And the first one, and the really main one that we really need to address for this problem, and we kind of saw it in the pattern in example 1 of the examples here, is that we only want subarrays that contain all of the distinct elements of the entire array. Right? How do we know that? Well, because we know there's going to be X distinct elements of the entire array, and we want for a subarray to be good, it to have X different unique elements. And so we want every subarray to have all the distinct elements or all X unique elements throughout the entire input array. And so what kind of does that lead to? Well, we can simply just pre-compute the number of distinct elements first and just find how many different subarrays have that number of unique elements. And so for every subarray, basically we check, does it contain that many distinct elements? If it does, it's a valid complete subarray. We increment the number of times we've seen one by one, and so on and so forth throughout all of those different possible options. But there's also something that you should note here. We can just check every single subarray using nested loops, and that would be big O of n squared, or sometimes even worse, worst case. We need to optimize that, obviously, right? Because I don't think n squared would work. Maybe 1000 squared might be less. I don't know. Maybe it's borderline TLE, and so we want to kind of optimize that. And so there's actually a very good optimization algorithm. It's a very common algorithm for such kind of nested loop implementations and optimizations. It's called the sliding window algorithm, to basically move across the array with pointers, and also use a frequency map to actually track how many distinct elements are in our current window while we still have a valid window. It's a very, very common pattern that we used before. Right, so let's go ahead and actually get into how we're going to really solve this problem in a high level. Basically, we're first going to use a set to actually calculate the number of distinct elements in the entire array, kind of like the pre-computing value. And we're also going to be using a dictionary or a hash map in Python to actually store and count the frequency of elements in the current window. We're going to be tracking and changing that continuously as we change our current window, as we iterate through the input array. And we'll also have, of course, those 2 pointers left and right, like we usually do for our sliding window kind of windows, if you will. And so how are we going to solve this? Well, first we want to pre-compute or determine how many distinct elements the entire array has. That's kind of our X value that we want all the subarrays to have that many distinct elements. And then we actually use basically still a nested loop, but for each starting index I, we're going to expand the window to the right, and we're also going to keep track of a count of how many unique elements we've seen. And as soon as the window contains all those distinct elements, we know that all the subarrays that start at I and end at it or after this point will be valid, because adding elements to our window is never going to hurt. Removing them also might hurt. Right, so let's go ahead and get into the code here. So what I'm first going to do is actually initialize or rather get the set of nums. In fact, before I've initialized my hash map, and so I'm going to call it total distinct. Now, what did we say about pre-computing of this problem? Well, really the only pre-computing part that we have to do is basically the number of unique elements in the entire input array. And a very neat way to do that is actually just get the set of the input array nums, because what a set does in Python is it basically just takes and extracts only the unique values, and it doesn't account for any duplicate numbers, right? So it's going to be the set of nums, but we don't care about which elements are unique. We only care about the number of elements that are unique, because that's our value that we want to kind of go for a subarray to be good. That's our target value, and so we want to get the length of that set to actually get the accurate number or total number of unique elements throughout the entire input array nums, right? That's going to be the number of distinct numbers that any complete subarray has to have to actually be, complete, or to be considered a complete. That's our kind of total distinct goal. Now, this is not really, needed. I just do this to help iterate over the array easier, just less typing. To be completely honest, I just store the length of our input array nums in n. Basically, it's just to help us loop through the array later on. Nothing too crazy here. And I'm also going to initialize my result. This is, of course, our output value. This is going to store our final answer. It's going to be the total number of complete subarrays that we actually increment and increment as we actually find more and more as we iterate through the input array nums with our window. So now let's actually begin iterating over the input array nums. So for I in the range of n, again, this is for that every single starting index or value I in the input array nums. Sorry, there should be n, not I. Where n is, again, the length of our input array nums. That represents the starting index of the subarray. I basically will actually initialize the frequency in each iteration to basically just be an empty hash map, where basically it's going to be counting or mapping how often each number appears in the subarray that starts at index I. Basically, it's a mapping with every single value to its corresponding frequency, hence we call it a freq. Now, let me also get the distinct count, because this is what we really care about to determine if the number of unique elements that are currently in a subarray, and if our current subarray is actually valid or not at this current iteration. So I'm going to call it distinct count. Basically, the number of distinct elements that we've seen so far in this current subarray, and of course, it's going to be initialized to 0, because initially we don't see any unique elements before we actually, start to build our window and iterate through the input array nums, right? So now let's actually begin the nested loop, or the inner loop here, to go from I to the end of the array, where I is, again, that starting index, and I'm going to call it j for my next pointer, and this is going to kind of mark the ending index of the current subarray. So for j in the range starting from I going up until n, again, where n is the length of our input array nums, where j is going to represent the ending index of the current subarray to go from I until the end of the array, all the indices in that range. And for every value j, for every potential ending index j in this, if first we want to check, okay, have we seen this element before at this current index j? If it's not in the frequency hash map, what does that really mean? That means, of course, we're seeing this for the first time. We haven't seen it before. It is one more unique element, because it's not in our frequency map yet. We haven't actually stored it in our current window just yet. It's the first time we're seeing it in the current window. And if that's the case, well, then we want to actually get frequency at nums at j, and we want to then increment it by 1, or rather set it equal to 1, right? Because we're initializing the value, or this new unique element in the current window, and setting its frequency to 1, because of course we just saw it's going to have a frequency of 1. We just actually encountered it in the current window. And now we also have to increase our distinct count for the current window, because guess what? We just found another distinct element in the nums at j. That's why we added it with a frequency of 1 and initialized as a key in our hash map for the current window. We just saw it for the first time uniquely, and we're also incrementing the distinct count because we actually discovered a new unique number in this current subarray. And so we're going to increment the number of distinct counts, or distinct elements that we found in this current subarray, by 1. So plus equals 1. But what if that isn't the case? What if nums at j is not in freq? What if we've already seen it in freq? Meaning, what if it already is in freq? It's not a distinct element. It's already in the map. And so if that's the case, we'll just want to very straightforwardly increment its frequency by 1. So nums at j in the frequency hash map by 1, because of course we're just incrementing its frequency or count. No change in the distinct count, since it's not a new number. We're just seeing it another time, and so we're incrementing its frequency in the current window by 1. Now, once we actually cover if this current element is seen or not, if it's unique or not, now we'll have another conditional here. What if our current element, or our current subarray, what if it's actually complete? How do we know if it's actually complete? Well, if the number of distinct elements in this distinct count, I think is what I called it, in this current subarray, if it's equal to the total distinct, that's again the total distinct elements in the entire input array, we know it's complete, and so that if the current subarray is complete, we want to increment res by 1 because we found one more complete subarray. That means the current subarray has the same number of distinct elements as the entire array, and so since it is a complete subarray, we increment our final counter or result by 1, indicating that we found one more complete subarray throughout the input array nums. And of course, once we actually increment our res accordingly, once for both loops actually are done executing, once the of course outer loop is done executing, once it terminates, well, we want to then return res, as it would actually have stored the final output of the total number of complete subarrays that have the same number of distinct elements as the entire input array nums in res, and of course we would output that as or return that as a result. So unless I made any syntax errors, this should be accepted, this should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So at a high level, how are we really solving this problem? Again, we're using that sliding window technique where we're basically looping through all the possible subarrays that start at each index I and counting how many of them are actually complete, meaning they contain all the distinct elements in the array using our 2 pointers I and j. And we're also using the hash map frequency to actually count the frequencies and track the distinct elements on the fly throughout all the windows at each real time, and that helps us actually determine the accurate number of total complete subarrays in the entire input array nums for every starting index I. So for the runtime complexity here, it still is big O of n squared. Technically, on average, it's somewhat optimized, but really, overall, on average, it's n squared because the outer loop would run n times, and the inner loop, worst case, would run up to n times as well, and each operation inside those loops are really just constant big O of 1 operations, like checking the hash map and adding hash map keys, but that's all constant time. That's not going to affect our complexity, and so overall it's big O of n squared on average for our runtime complexity. And for our memory or space complexity it's really just linear big O of n. Why? Because the really only extra data structure or auxiliary memory that we're using is this frequency hash map, where basically it would store up to n elements in the worst case, and so of course that is also going to be linear or big O of n for the space or memory complexity. So again, like I talked about in the beginning of the video, even though it is n squared, the reason why it's still actually accepted on Leetcode and it's still, one of the more efficient solutions is because n is small. I kind of glossed over this in the initial part of the video, where we actually have rather small input constraints, giving us more room to work with. N squared still technically works, and so when n is going to be less than or equal to 1000, typically Leetcode does actually permit n squared solutions to still be, valid. It won't give us a TLE. Right, so if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.